Hello, this is Andy from the Engineers Academy, and in today's video we're going to be looking at how we determine the enthalpy of combustion when we combust hydrocarbon gases such as methane, ethane and propane. Now, the approach that we use for this is by using standard molar enthalpy of formation values for the products and the reactants in our equation. I'll explain what I mean by the products and the reactants in a moment. But in the top right hand corner we have a table displaying standard molar enthalpy of formation values. At the top of that table we have the standard molar enthalpy of formation for water. Now you'll notice in brackets there we have water as a gas or water vapour, and the standard value there is minus 241.8 kilojoules per mole. The reason that value is negative is because when we form that water molecule we have an exothermic reaction, which means energy is going to leave the process. The reason we treat water as a vapour in these calculations is because when we have a combustion process, the temperatures are relatively high, so the water is going to remain as a vapour rather than converting back to a liquid. We also have standard molar enthalpy values of formation for carbon dioxide as a gas. The oxygen molecule, where you'll note the value is 0, because an oxygen molecule, O2, is in its lowest energy state. And finally, we have the standard molar enthalpy of formation for a methane molecule, an ethane molecule, and a propane molecule. So the next thing we need to consider then, if these are enthalpy of formation values, is how we determine the enthalpy of combustion. Well, we have a general equation here, and the general equation for the reaction is that the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of our reactants. Now, to explain this in simple terms, the products are what we get out, so on the right hand side of our equation are our products, and the reactants are what we put in, so the left hand side of our equation. In this instance, our reactants are the methane molecule and the oxygen molecule, and our products are the carbon dioxide and water molecules. So before we can do any calculation work, we need to make sure that our equation is balanced. We have each of our products and each of our reactants there, but we need to ensure that this equation is balanced. Now, the way that we approach this is, first of all, we need to make sure our carbons are balanced. Well, on the left-hand side, we have one carbon, and on the right-hand side, we have one carbon. So our carbons are balanced. Next, we need to balance our hydrogens. Well, if we look at the left-hand side, we have 4 hydrogens, but over on the right-hand side, we only have 2 hydrogens. So what we need then is 2 of this group, 2 H2O, because now our hydrogens are balanced. We have 4 on the left and 4 on the right. Now, fortunately, by having 2 H2O groups, we also have 2 oxygens. Therefore, the final step of balancing our oxygens, we have 2 on the left and we also have 2 on the right. So now we can come on to calculating the change in enthalpy of that reaction. Now we have to be a little bit careful here because we have negative values for our standard molar enthalpy of formation values. We start with the products, which are on the right hand side, and we have one CO2 molecule. So using the table, for one CO2 molecule, we have an enthalpy of minus 393.5. Note that the units are kilojoules per mole. So we have minus 393.5. We need to add 2 times the enthalpy for our water molecule, and again take care here, because for the water molecule we have minus 241.8. And then we need to minus our reactants. Well, minus, and we have a negative value here for the methane, minus 74.8, so minus 74.8. So we have products here, minus reactants here. So when we input those values, we get an enthalpy for that reaction equal to minus 802.3 kilojoules per mole. Note that the units there are consistent with our units for the standard molar enthalpy of formation. So effectively, that's the amount of energy that's contained in 1 mole of methane. Now, practically, that's not particularly useful. Instead, we would prefer to have the amount of energy contained in 1 kilogram. So we can use something called the molar mass. Now, the molar mass of methane is 16 kilograms per kilomole. We need to take a little bit of care here because this energy value that we've calculated is the amount of energy in 1 mole, whereas this value of 16 kilograms is the mass for 1,000 moles. But if we divide that by 1,000, then we get the molar mass of methane as 0.016 kilograms per mole. So now we have something we can work with. A value that's useful for any fuels is known as the calorific value. And we'll abbreviate this to CV. Now we have calorific values for all different fuels. We have them for solid fuels such as coal, we have them for liquid fuels such as petrol or diesel, and in this case we have them for gaseous fuels such as methane, ethane and propane. Now we can determine the calorific value now because we know the amount of energy stored in 1 mole of our fuel. The amount of energy stored in 1 mole is 802. Just take care here because it's 802.3 kilojoules. So 802.3 is 802,300 joules. Going to work in SI units. We know the mass of 1 mole is 0.016. So we can calculate our calorific value. And in this case, it comes out as 50.14 megajoules per kilogram. Now, if you were to run this through your calculator, you would get 50.14 times 10 to the 6 joules as our SI units, which is the same as 50.14 megajoules. So that's the amount of energy stored in 1 kilogram of our fuel. So how would we use that value? We know how much energy is stored in 1 kilogram of our fuel, but how would we use that information to determine, say, the mass flow rate of fuel into a combustion chamber? So thinking back to earlier tutorials, we calculated the amount of energy needed within our combustion chamber in order to produce required temperatures of air-fuel mixture. Once we knew the amount of energy being supplied in our combustion chamber, and we calculated the amount of power output from gas turbine plant, we were able to calculate the overall efficiency of that plant. Now for the purpose of this video, I'm going to reuse the value of Thioin, or the heat input, from the previous video. Now our heat input value there was 966.1 kilowatts. Or in SI units, 966,100 watts. Let's create a little more space. So now that we know the amount of heat energy that's being supplied to our combustion chamber, we can determine the mass flow rate of fuel into the combustion chamber. We're going to assume that the combustion of the fuel is 100% efficient, so that means all of the energy that's being supplied in our combustion chamber must be coming from the combustion of our fuel. We have a relatively straightforward equation here. The heat energy in equals the mass flow rate of our fuel times the calorific value of our fuel. Now this would make sense because it's the rate that energy is being used or burned up within our combustion chamber. If we wanted to determine the mass flow rate of our fuel then, all we would need to do is rearrange this. So Thioin over the calorific value. And we need to make sure we work in SI units, but we have 966,100 divided by our calorific value, 50.14 times 10 to the 6, which gives us a mass flow rate equal to 0.01927. And the units there will be kilograms every second. If we multiply that by 1,000 then, we get 19.27 grams per second. So within our combustion chamber, we're combusting 19.27 grams of methane every second in order to produce 966.1 kilowatts of power. So we're going to repeat everything we did previously, except this time we're going to be doing it for the gas ethane, and the formula for an ethane molecule is C2H6. So we start by balancing our equation. Now in order to balance our equation, we begin with the carbons. We can see that we have 2 carbons on the left-hand side, meaning we need 2 lots of our CO2 group. Next we balance our hydrogens. We can see that we have 6 hydrogens. Well, over on the right-hand side, we only have 2 hydrogens. So we need to multiply that group by 3. 3 times 2 gives us 6 hydrogens. And the last thing we balance is our oxygens. Well, if we look at our CO2 molecule, we've got 2 times 2 oxygens, which is 4 oxygens. And then we've got 3 times 1 oxygen, which is an additional 3 oxygens, giving us 7 in total. Now, there isn't an issue. It just means that we're going to need 3.5 of our O2 group on the left-hand side. So we're going to have plus 3.5 of our O2 group. So now that equation is balanced, we have the same number of carbons, the same number of hydrogens, and the same number of oxygens on each side. So now we can begin our calculation. Recall that the change in enthalpy of this reaction is the enthalpy of our product, or the enthalpy of the right-hand side, minus the enthalpy of our reactants on the left-hand side. The enthalpy of our products is 2 times the CO2 group. Well, the CO2 group is minus 393.5. To that we need to add our other product, which is H2O, so we've got 3 times minus 241.8. Now to that, we're going to subtract everything on the left-hand side. Now on the left-hand side, we have 1 ethane molecule minus 84.7. Now I didn't make this clear in the previous example, but to that, we would be adding the enthalpy of formation of an oxygen molecule. Well, if we refer to our table, we know that the enthalpy of formation of an oxygen molecule is 0. O2 is already in its lowest energy state. So in effect, we're adding 0, so we can disregard the oxygen. Now, if we run those numbers through our calculator, we have 2 times minus 393.5 plus 3 times minus 241.8, and then we have minus 84.7, which is the same as just plus 84.7. Now that gives us a change in enthalpy there equal to minus 1427.7 kilojoules per mole. So next then, we're interested in our molar mass of C2H6. Well, the molar mass of C2H6 is 30.1 kilograms per kilomole, or 0.0301 kilograms per mole. So our calorific value then is the energy per mole, 1427700 in joules, divided by the mass per mole, 0.0301, giving us a calorific value equal to 47.41 megajoules for every kilogram. And if we use the same Phi-in value as for our previous example, we have Phi-in equals 966.1 kilowatts. We know that the energy in our combustion chamber is the mass flow rate of the fuel times the calorific value. And so we know that the mass flow rate of the fuel is the energy in divided by the calorific value. Our energy in is the same, 966,100 in watts, SI units. Our calorific value is 47.41 times 10 to the 6 joules per kilogram, giving us a mass flow rate equal to 0.02038 kilograms per second, multiplying by 1,000 gives us 20.38 grams per second. So just to recap then, we are able to use our standard molar enthalpy of formation values, so we're able to determine the amount of energy that's released when we combust 1 mole of our fuel. We also know the mass of 1 mole of our fuel, so we can determine the calorific value, which is the amount of energy contained within 1 kilogram of our fuel. If we were to combust 1 kilogram of our fuel, in this instance we would release 47.41 megajoules of energy. We've used that information because in an earlier tutorial we knew how much energy was being supplied in our combustion chamber. We're assuming here that our combustion chamber is 100% efficient. So using the information about the energy supplied to our combustion chamber and the energy contained in 1 kilogram of our fuel, we're able to determine the mass flow rate of fuel into our combustion chamber in order to sustain that combustion process. So I hope you found this video useful, and thanks for listening.